My name is Melissa Telong, and with my colleague Stephan Pirskawetz, we will present the project Lebe Digital. So the term Lebe of Lebe Digital stands for Lebenszyklus von Beton in German, which is translated in English as concrete life cycle. Therefore, the project is about developing an ontology for the concrete production process chain. Before we dive into the core of the project, let's start by introducing our team, the material we have been working on, and also the project goal. So, Lebe Digital is sponsored by BMBF under the supervision of the platform Material Digital. We are working together with 3 cooperation partners. The first one is the Federal Institute for Materials Research and Testing, the BAM, where we are now. And BAM focuses on the material side and also the modeling and simulation. We also have another department which works on the IT architecture. The second cooperation partner is the Karlsruhe Institute of Technology, which works hand in hand with BAM on the material side. The third cooperation partner is the Technical University of Munich, which focuses on the calibration. So, as mentioned before, the project Lebe Digital is about developing an ontology for the concrete production process chain. Therefore, the material we have been working on is concrete. Concrete is a very complex material for different reasons, not only because of the diversity in the base materials and in the component designs, but also because of the high complexity of the recipes. Indeed, concrete is not made no more or even lesser than it used to be. It's not only made with cement, water, gravel, and sand, but nowadays we want to achieve more characteristics. We want the end hardened concrete to have specific characteristics, and this is why we usually nowadays we use different types of admixtures and different types of additives into the concrete to achieve the characteristics, the properties that we want to have according to what way we want to use the concrete. For example, you can see on the right side here, you can see different types of ashes and starches made from food residues. For example, rice husk ash, cassava peel ash, cocoa pod ash, which were made and incinerated here to put inside the cement. So the recipes of cement, of concrete that we can have is actually almost endless. On the other hand, we have a high complexity of the manufacturing process. The manufacturing process, for example, of a lightweight concrete is different from the one of a precast concrete. It's different from the one of a pre-stressed concrete. Because, for example, if I have a construction site where everything is made out of precast concrete, it means that the concrete is manufactured. It means mixing, molding, curing. Everything happens in the manufacture, and then the end concrete is just brought it on the construction side. And this manufacturing process of the precast concrete will be totally different of the one for a ready-mix concrete or Transportbeton in German, where concrete is brought out on the construction site in hydration. Like, it's still hydrating, it's not yet hardened. And also the manufacturing process is different according to the fresh concrete characteristics we want to have, like the workability or even the density of the fresh concrete. We also have a diversity in molding designs and also the time dependency of all properties in concrete. The cement hydration begins when water comes in contact with cement. And when it happened, the concrete goes from a kind of unstable stage, which is mostly kind of liquidy, to a more stable stage where concrete becomes harder. So all these parameters has to be taken account while building the ontology. Collection and storage of experimental data. So the pictures you are seeing right now is an overview of what happens in a concrete lab. Every concrete production starts with a mixture design. So we have the mixture design where parameters are written, like the water-cement ratio and even the different components with their quantities that are to put inside a concrete. We also have, as you can see on the left side, a form or a mold for the concrete. Then what happens is that we mix the concrete, and then before putting it inside the form, there are some characteristics, some tests that needs to be conducted to see if the concrete is in good health, I would say. So, and for that, we do tests, like sometimes, it's not every time, like settling tests, or we need to weigh the fresh concrete, and those are information that also needs to be stored. Because the lab workers, sometimes they wear gloves and they are busy inside concrete, it's not always easy to take a computer and open an Excel sheet and write information. So what they do is that they just take a piece of chalk and they write on the board. But what happened afterwards, for example, if they forget to put those information back into an Excel sheet, so all this setup raises the questions around how are data collected, how are data stored around the concrete production, which brings us to our project goal. So we want to have an ontology-based collection of data and metadata in TripleStore. We also want to link existing data, experience-based data, experimental data, and simulated data. We also aim to combine both the material composition and the geometry optimization of precast elements based on simulation workflow. And also we want to do model calibrations. So overall, what we aim is to have a material database where concrete specific characteristic values and models are structurally integrated. So this was for you to have an overview over the project, over the team, on our material and what we have as a goal. Now I will pass the baton on to my colleague that will tell you more about the ontology development.
Let's start with the ontology development, but before we talk about our concrete production and testing ontology, we have to define what we mean in our project Liebe Digital when we talk about an ontology or a knowledge graph. In our project, we defined an ontology as a collection of hierarchically structured concept-based classes and subclasses, supplemented by a collection of properties describe relations between individuals. And in our ontology, we added here a set of generic individuals, mainly to describe different types of cements here. But these generic individuals can also be found as units, for instance, in the QDT ontology. At the end, it's a kind of construction set for knowledge graphs, and these knowledge graphs then built from this ontology. And in our understanding, and knowledge graph is a collection of individuals sorted into the classes of the ontology and linked by the properties of the ontology. I think that we started, like every other project, with a list of terms and definitions. In our case, in the field of concrete technology, is mainly a simple Excel sheet that contains a lot of labels, and these labels later on, or most of these labels later on, become classes in our ontology. And these definitions of these labels or classes at the end are, or describe the concepts of these classes. Sources, we have done that in German and English to be a little more, the ontology development in the field of concrete is mainly for Germany, but I think it's useful to have it also in English. And sources for the labels, classes, or terms and definitions are mainly standards in the field of concrete technology, and one very important source is the so-called betontechnische Daten. It's a kind of guideline that is annually updated and that guides experts through the jungle of a lot of standards, and and explains concrete technology in general. Can be found on the internet on different sites. And our first attempt to develop the ontology was to describe, or generic description was a generic description of the processes like measurement, like the measurement process of measurement of the elastic modulus, for instance, or the measurement of compressive strength of concrete. And we use the basic formal ontology in the beginning and the CCO. But it turned out that this attempt was too complex at the end, and inside the project, the partners were not really interested in the description of these measurement processes. And therefore we started a user story analysis, and there turned out that inside the project, the partners are mainly interested in the description of the raw data. These raw data were needed as an input for the simulation models to recalculate the experiments. For instance, the elastic modulus experiment on a concrete specimen, and to calibrate the models this way. And the partners from the industry were mainly interested in the calculated results of the experiments, not in the raw data. Here, for instance, the compressive strengths of different mixtures over a certain period of a production of concrete, and it can be used to analyze, for instance, the influence of changing raw materials, changing environmental conditions, or maybe to optimize mixtures regarding the CO2 footprint, or reducing the costs of mixtures and so on. Based on these findings, we restarted the development of the ontology, and it's now based on the PMD core, the version 2. And to keep it as simple as possible, we focused now on two main classes inside the PMD core. It's the class object and the class value object. One main object in our ontology is a mixture. That, of course, is an engineered material in the PMD core, and it consists of raw materials. And here we added some classes describing our raw materials, for instance, fibers, aggregates, and inside the inorganic materials we have the cement, for instance. And this mixture is then characterized by value objects. And for the mixture, it's mainly the content of the raw materials inside the mixture. For instance, the cement content of the mixture could be, let's say, 400 kilograms per cubic meter of concrete. And another anchor in our ontology is, or anchor object is a specimen that fits to the concept of Probe in the PMD core, and again it is characterized by value objects, and for specimens such value objects could be a diameter of the specimen, or elastic modulus, or the characteristic compressive strength. And at the end, that characterizes the concrete itself and also the mixture. And now we have the basis for the development of the knowledge graph, and how to come from the knowledge graphs, from the raw data to the knowledge graphs will be explained by Melissa.
Yeah, thank you. So now it's important to understand how we go from the raw data to the knowledge graph. So everything starts with the raw data. So the raw data is any type of results that come from a lab or from a company that conduct, for example, a test on concrete. So we receive the data in different formats. It's possible according to, because different types of companies, different types of labs have different types of format and different types of structures, even in the same format. So here you can see two examples of data that, the .dat file and also the .excel file. So what happens is that we want the data to be kind of standardized, and for that we generate a standard JSON file based on a Python script. So we write a Python script that converts the raw data, in no matter the format, in a standardized JSON file where data and metadata contained in that raw data are stored. And by doing that, we also generate an ID. So just after that, the second step, the other step is we have the data and the metadata that are stored into the JSON file. Now we have what we call the knowledge graph template. The knowledge graph template, you can see it as a box. So we have a box that is that contains nothing inside, and we want to put the data and the metadata stored in the JSON files into this box, knowledge graph template. And so we have the knowledge graph template, and to do this putting of data and metadata into the knowledge graph template, we use another Python script. So these Python scripts make from two data, so JSON file and knowledge graph templates, another file which is a knowledge graph then. And this putting of metadata and data into the boxes which are the knowledge graph template, to convert it in a knowledge graph is called mapping. So to say, the data and metadata are mapped into the knowledge graph template, and it builds then the knowledge graph. So how is this knowledge graph template actually made? The knowledge graph template, which in this case are turtle files, are made out of the draw.io files. In the draw.io files, we want to have a certain type of structures, because we don't only want to have boxes where metadata and data are stored without any structure. So in the draw.io file, we kind of have a structure with classes and subclasses. And these draw.io files is based on the concrete production and testing ontology that Stephan Pirskawetz just showed some minutes ago. So you can see, for example, in the class concrete, you have different type of concrete types, like lightweight concrete, fast beton, fast concrete, and so on. So the draw.io files based on the concrete production and testing ontology, which enables us to have not only data and metadata stored anyhow, but they are stored according to a certain structure. So we have generated so far 7 knowledge graph templates. As I said before, the concrete production is very complex, and the manufacturing process differs from a concrete type to another one. So for now, we focused on these 7 knowledge graph templates. The first one is the mixture design. The mixture design is the base of the concrete production, is everything around what will be inside the concrete. The second knowledge graph templates we are working on is the mixing process. The mixing process contains information about what do we use first, what do we put first in the mixture. Do we put water first, or do we put cement first? And for example, how long do we mix on the first step, the second step, and so on. And these are based on the norms. The third one is the heat of hydration. The heat of hydration is made on a fresh concrete to know how exactly the heat is released over the time. The fourth one is the hardening and storage. The fifth one is the specimen, and in this case it's very important to understand what we call specimen, because we will have an example on the specimen and the compressive strength very soon. So the specimen is concrete that has been put inside a mold, and then that has been on mold after a certain type of hours, a day generally, and then after that it has been cured into a specific round with specific atmospheric condition, and this is what we call specimen. And after 28 days. Then the other knowledge graph template we are working on is the compressive strength, and the last one is the emojoule. So now let's take an example of the knowledge graph development and on the specimen and compressive strength. So I mentioned before that everything starts with the raw data that we receive from any lab. We receive the raw data. The raw data looks like this. What you see on the screen is the right side and the left side. It's the same informations, but stored in different types of formats. On the left side, you have the .dat file, and on the right side, you have the Excel file. So what you see in green is actually every information needed to calculate the compressive strength. What we do is that we do the extraction of data and metadata in 2 steps. So the first step is the data extraction from the rows, for what you see in blue on your screen. So we have information like the diameter, the height, or the weight of the specimen, because of course we need a specimen to be able to do a compressive strength. This is what both of them are linked. It's the same. If we also need a specimen to do an E-model test, but in this case, in this example, we focus on the compressive strength. Now we also have a data extraction based on a Python script which extract information of the columns, especially the fifth column, which contains the information about the compressive strength that we want to calculate. So now we are on the second step where we want to extract the data and the metadata and to generate an ID using a Python script. So this is the extraction of the columns where the results of the Druckfestigkeit, of the compressive strength are. So this script extract metadata from the vertical lines and stores them in a CSV file. And this extraction here, what we have as results as extraction, will be used then afterwards and then stored into the knowledge graph mapped. So this is the other script which extracts information always from this raw data file, extract information from the rows, so to say. So it extracts data and metadata and store them in two different JSON files. So we have a JSON file containing data and metadata of specimen, like the diameter and unit. So it's always the value first and then the unit separately. We have the height and everything else needed for the specimen. And then we have the compressive strength metadata JSON file, which contains information about the compressive strength. Now we are reaching the third step, which is to create, so to say, a box, what I call a box, but it's a knowledge graph template where the data and metadata will be stored. So it looks like this for the specimen. So like I said, we have the class specimen, for example, which has different types of things that are needed to recognize, to link to the specimen. So we have the diameter, the thickness, the length, the width, and so on. But we also have an identifier. For example, this one is a machine-readable ID. So a machine-readable ID is different from a human-readable ID. The human-readable ID, for example, if I do a test today, the 2nd of February 2024, if I do a test I do a specimen and I have a lightweight concrete, I may write lightweight concrete 2nd of February 2024, human readable, but the script also generates a machine readable ID, which is very unique to the specific specimen. And to have the specimen, of course, we need to have a mixture, but the mixture, the ID of the mixture is different from the ID of the specimen, because we can have a batch. It's like when doing cookies, you do a batch and then you pour into different types of molds. So I can do a whole batch of concrete and then put it in different molds, which is then, at the end we have then different types of specimen. So now, like I said, here is the draw.io file. This is the knowledge graph template, and this is what I shown before, the JSON file containing the data and metadata that we had from the raw data, that we have extracted from the raw data. So just for you to see how it is, we have the diameter here, the value. This is the value here that we have. Everything you see in orange they are like placeholders where the actual data will be put into. And the unit, we know that for a diameter, the unit doesn't, it's in the meter or millimeter. Yeah. So this is the same for the height. So now you can see the correlation between the knowledge graph template and the metadata. So the knowledge graph template of the compressive strength looks similar, but as I said, in order to be able to proceed to a compressive strength, we need a specimen. This is why in the knowledge graph template they are kind of linked together. But it's almost the same. We have the value here and we have the units here, and then afterwards we come to the other step. The other step is that we have the knowledge graph template, kind of the boxes. We need to put the data and metadata into the knowledge graph template. For that, we use a Python script, and that will make out of these two data files one data file, which is called the knowledge graph, and the whole process is called the mapping. So now what we have created so far is one JSON file containing data of the specimen. We have knowledge graph template concerning the data of a specimen. What we do is with this mapping script, these two make this one specimen mapped. And it's the same for the compressive strength JSON file and compressive strength knowledge graph. Out of two, we have this one, the compressive strength mapped. So the mapped data contain all the information about the data that we have extracted from the raw data. Here you can see as example, these are the knowledge graph templates. So the boxes which are not yet filled, you can see everything you see and underline here is where the data needs to come. And then now I will show the mapped file. You can see that they are filled with informations. So far we have seen how to go from a raw data to a knowledge graph templates. We will now talk about where we are now and what are the next steps.
As the next steps or next slides are mainly a summary of this, what we have shown before. Work status is that we, as shown, developed a list of terms and definitions in concrete technology. We developed some user stories and a main domain-specific concrete and production and testing ontology. We also developed a set of knowledge graph templates and the scripts to map the data on these templates, and we created a minimum working example that contains mapped data or the process of mapping data and linking the different knowledge graphs that Melissa showed together to one knowledge graph or to one triple store at the end. All these points here are under progress. We regularly update our terms and definitions in concrete technology, for instance, and we are also still working on the on our ontology and the knowledge graphs and the mapping scripts and so on. The project itself extended until January next year, so we will have 1 year left to do or to go the next steps here. And the challenges here or the main challenge here, I would say, is to develop a workflow for an automated data import from raw data to the triple store, and In this course, we will provide some raw data for testing of the workflows and also some typical queries for the triple store. And I hope that we are able to publish that so that everybody can play around a little bit with these triple store, the queries and so on, and the raw data, maybe upload own raw data. In future, we will need a user-friendly interface for our triple store, I think, to bring it in practice and use. We have to develop some additional knowledge graph modules. There are still some missing. And of course, we will update the concrete production and testing ontology to the next versions of the PMD core. And in this course, we will try to restructure the CPTO and use the processes of the PMD core to hopefully better describe the production process, the production chain of concrete itself. And we will present and discuss the results of our project in the final colloquium end of the year.